Okay, so the speaker today is Katz, and he's going to tell us about Hamiltonian truncation. All right, go ahead.
All right, thanks. It's a pleasure to talk at our family meeting. Uh, and I'll be talking about some new work that I've done together with Nikhil, Zuhair, and Matt recently. Just came out last month. And it's our attempt to basically take Hamiltonian truncation methods and push further into 2+1 dimensions and try to obtain dynamical quantities. So, the picture that we are kind of trying to realize is really just a way of approximating eigenstates of the Hamiltonian. So that's kind of the goal. The idea behind approximating the eigenstates of the Hamiltonian is to kind of, if you want, go back to your childhood and it was an innocent time and you were told that quantum mechanics, you're given a wave function and your task is to be able to evolve this wave function in time. And so by doing this, you are capturing the dynamics of the problem. And if you are able to do it, then this opens up the possibility of calculating all sorts of interesting observables. Like, for example, you can calculate 2-point functions of local operators in time. That's related to all sorts of things that can be measured. In, for example, quantum critical phenomena, as well as in particle physics contexts. And so for now in this work, mostly I'm going to talk about correlation functions in time that are measured in the ground state. But in principle, it's also quite interesting to calculate correlations in time in excited states. And once you have some subset of the spectrum calculated, you can in fact consider excited states, not just the ground state. And that opens up the possibility for exploring non-equilibrium dynamics, thermalization, the eigenstate thermalization hypothesis, hydro. You could take states of large charge. So there's lots of things that one could do in principle. So it's a worthwhile goal to try and do this. Also, it might be interesting once you are finding the eigenstate to measure properties of the eigenstate. So, for example, if you have some sort of bound state, you can measure aspects of this bound state. So perhaps the proton is something dear to your heart, part of your lifestyle. So you might be able to hope to measure something like the PDF of the proton. So developing these kinds of techniques, I think, are kind of a worthy goal. So how would you apply Hamiltonian truncation to quantum field theory? Well, the idea is that you take the Hamiltonian of the quantum field theory, which consists of two parts, a part which is free or under some control, it's some integrable part, and then you perturb it by some interactions or by some relevant terms. And so then the idea is that you take the QFT Hilbert space, which you've written down in some sort of basis. For example, you could just take the Fock space states in finite volume, or another very popular technique is to take CFT states on a sphere. So you take the Hilbert space parameterized in some way. We're going to take a slightly different parameterization of the Hilbert space. And then you truncate to a finite subspace. So again, most typically what one does here is you take the eigenstates of H0 and you consider the eigenstates of H0 whose energy are below some truncation energy. So that's now finite subspace. And what you get is now Hamiltonian, which is a finite matrix, and you diagonalize this matrix numerically, and that gives you some approximation to both the eigen states as well as the energies. Okay, so what are the advantages of this method? Well, the nice thing about truncation is that typically you can keep a subset of the space-time symmetries manifest. So unlike sort of some lattice technique where you might have mixing of operators that have different quantum numbers under space-time symmetries. Here you can be um, more careful about that. You can really separate them out because some of the space-time symmetries are unmanifest. In some sort of moral sense, it's kind of satisfying because you're including the degrees of freedom of the quantum field theory of interest, and you're not adding additional degrees of freedom, like lattice degrees of freedom. And energy truncation, in a certain sense, seems economical because especially if you're thinking of a relevant deformation, it makes sense that if you're interested in the low energy eigenstates of the full Hamiltonian, that is the H0 plus V, that those should be made mostly of the low energy states of the original Hamiltonian. And so in a certain sense, that's kind of economical, but there are also disadvantages to this approach. And so the main one is basically a lack of locality when you're using energy truncation. So one thing that the lattice, for example, has for it is that it has sort of a momentum or like a cutoff effectively. It is the locality is kind of built in. And one of the things that we're going to find, and that's one of the problems that you face when you're trying to extend the truncation method to say higher dimensions typically, is you cannot renormalize the theory with just local counterterms. So that's kind of problem one. And so you have to come up with a more complicated procedure for renormalization. Now, the other issue, which is not so much a disadvantage, but is kind of a challenge, is that you are insisting on actually approximating the eigenstates of the Hamiltonian, as opposed to, for example, when you calculate a correlation function and using, let's say, Monte Carlo methods, you are effectively at finite temperature, and therefore you're not actually separating the ground state, say, from other states. You are kind of in an ensemble. And so, insisting on actually calculating a particular eigenstate is sort of a challenge. And typically the issue is just that for a given volume and a given truncation, you have an exponential growth in the number of states. And so this is kind of, whereas problem one is just a problem in principle that, you need to solve. Problem two, I guess, is more computational, something that maybe your grandchildren are not going to have. But in practice, you have to worry about this when performing an actual calculation, whether or not there are just too many states for you to manipulate them efficiently. Okay, so problem one and problem two are going to be like sort of the typical problems that we face when we think about Hamiltonian truncation. And in particular, the question is really, given some dynamic range that you're interested in, you want to have some dynamic range to do physics, how many states do you need to be able to get to that kind of dynamic range? Okay, so these are the issues. And so we go to therapy to try to figure out how to deal with our issues. And so we're going to consider this sort of 2+1 dimensional lab for truncation. Our favorite spherical cow is, of course, phi to the fourth. That's the first thing you try when you are trying to figure out some new technique. And the nice thing about this particular model is, well, first of all, it contains divergences. So you do have to figure out how to deal with this more subtle version of renormalization. There's a linear divergence associated with the vacuum energy, and there's a log divergence associated with the mass. So that's something you need to deal with. And also you do have a more rapid growth in the number of states than, for example, you have in 1+1 dimensional context. So this is another challenge that you need to be able to get to interesting physics, with as few states as possible. On the other hand, the positive side is that sort of if you're able to address these two challenges, then you know something about what this theory is going to do. So for arbitrary coupling, it's something non-perturbative, and it's hard to compare to anything. But if you tune this theory, it's supposed to have critical behavior, which is characteristic of the 3D Ising CFT. So it's supposed to have a fixed point. And so indeed, this is something that you can look for. Okay, good. So let me explain first the issue associated with problem one. So why is it that you need state-dependent renormalization? So I'm going to use the example of a mass contribution, just the mass renormalization for an n particle state. So imagine you have some n particle state right here, and imagine that you are considering a contribution to its energy shift, which we associate with the sunset diagram here. This is just the mass shift. This is a change of the mass parameter. So in this diagram, what I mean by this diagram is I mean to indicate just a second order in kind of old-fashioned perturbation theory, where I have an n particle state, and this n particle state mixes with an n+2 particle state, and there's some shift in the energy, right? So, in a usual field theory calculation, we don't really care about all these bystanders, these additional particles, and we just concentrate on the loop, and we put a cutoff on the loop, and we get some sort of local divergence, and we renormalize with a local counter term. But the problem here is that when we perform an energy truncation, we're actually truncating on the energy of this intermediate n+2 particle state. And what that means is that these loop momenta, these loop energies, are sharing their energy with the other spectators. And as a consequence, the energy available to just this loop is not lambda, but it's lambda minus whatever are the other energies carried by this spectator. So in other words, the actual energy cutoff or seen by the loop is sensitive to whatever else is going on. In particular, it depends on the details of this intermediate state, and that's what gives you the complication. That's what the complication comes from in truncation. And so, okay, as long as the theory is finite, it doesn't really matter if there's this finite shift to the cutoff. Corrections goes 1 over lambda, and those finite shifts are subleading. But the second that you have UV sensitivity, you have to think about whether or not these finite shifts are actually going to impact the physics, right? But what is very clear is that the second that you have these finite shifts, you can't just renormalize the theory with a local counterterm, because the local counterterm obviously doesn't know anything about the other states that are also propagating there in the diagram. And so, and the situation can become more and more complicated as you go to higher and higher orders in perturbation theory. So for example, you can think of this sort of process. And again, I'm thinking of this as some contribution to standard sort of old-fashioned perturbation theory. And so here you're inserting a complete set of states. So you're starting with, say, a 5-particle state, and here you're transitioning to, you go from a 5-particle state to like a 7-particle state, and then then you can go to a 9-particle state, and so on. So these cuts are sort of the insertion of the complete set of states in between. And so the point is that when you have this kind of sensitivity, you're actually sensitive precisely to all the energies of the different spectators here. So this bubble is actually sensitive to what's happening here and here and here and here. And so in practice, this can mean that renormalization becomes complicated, and you potentially need new state-dependent contributions at every order in perturbation theory. So that's one of the reasons that that people have not pushed Hamiltonian truncation as hard in higher dimensions, but now I think the good news is that we have fixes for this problem. So first, there's I should say a nice paper by Elias Miro and Hardy where they proposed a solution to this particular problem in the context of equal time quantization. So there, the issue is not actually the mass renormalization, it's rather just the linear divergence associated with the vacuum energy. That's the main problem that they have to solve. And they propose a solution to this problem. We're going to take a different approach. So it's technically going to be orthogonal. So, I refer you to this work if you want to see they're also studying phi to the fourth theory, and so it's kind of also nice because it's a overlap with the same model. But our approach is going to be different. What we're going to do is we're going to use Lightcone quantization. So in Lightcone quantization, you have sort of one Lightcone direction you choose as time, and the other Lightcone direction you put together with the rest of the spatial directions, and you think of this as space. You quantize the theory on a particular Lightcone slice. Your Hamiltonian, which is conjugate to this time, is P plus, so that's your, and the frame that you're in is a frame where you have some positive P minus, and we're going to choose the momentum in the perp direction to be 0. So all of our states are going to be positive P minus states. And so as a result of this, the vacuum state is just not affected by the interaction because all states have positive P minus, whereas the vacuum has P minus equals to 0. And so this is sort of your spatial momentum. And so interactions preserve that momentum, and therefore the vacuum remains trivial, right? So just by doing this, you make your life a little easier because you don't have the linear divergence associated with the vacuum energy. But as we will see, we still have to worry about the log divergence. Now, of course, one should be careful about using Lightcone quantization. In general, Lightcone quantization, you should obviously, the obvious question is what happens when you have phase transitions. I mean, if you're really saying that the vacuum is trivial, you know that that cannot be the case once you cross a phase transition point, and then indeed that is true. But at least if you stay on the same symmetry side, that is, you stay on the symmetry preserving side of this theory, then you're safe. And in particular, even though we haven't done the analysis yet for this 2+1 dimensional model, the same model, the phi to the fourth one model in 1+1 dimensions, we can actually map the Baire parameters from equal time to Lightcone. So this is work that I did together with Liam and Matt, and it was using this technology developed by the CISA group. And so there we were precisely able to map using Borel resummation the equal time parameters to the Lightcone parameters, as long as we stayed on one side before the phase transition. After the phase transition, that breaks down. And so we are in this work, we're just going to be working in the Z2 symmetric phase. Okay, so log divergences is something that we do have to worry about on the Lightcone, and they have their own specific kinematics. That's why it's a bit different. It's different in equal time. You don't have to worry about log divergences, but on the Lightcone you do. So let's just look at this again. This exact kind of contribution. What happens is that I have some state in here. So I have an n particle state, and it mixes with an n+2 particle state. And let's say I put a cutoff on the p squared invariant momentum, which in our frame is just a cutoff on the product of p plus p minus of this intermediate state, right? And so if I do that, then I essentially adding up all the Lightcone energies of these particles, I'm putting a bound on their total Lightcone energies, which again means that if I'm asking what is the Lightcone energy available to this loop, then there's a shift, there's a finite shift associated with the other energies that these guys are carrying. But also, once I actually calculate the the invariant which is going through this loop, that is to say, I calculate not p plus, but rather p squared, right, which is the loop in momentum, invariant momentum here, then what happens is I multiply this thing times the momentum associated with this particular particles, because the dispersion is 2p plus p minus. If I took this 2p plus, then the p minus that I have to multiply by is the p minus of this incoming particle here. So besides having a shift in the energy, we essentially get this additional multiplicative constant, which just depends on the Lightcone momentum of this incoming particle. So written in terms of sort of a Lightcone momentum fraction, so if I define the momentum fraction carried by this guy as x, then what happens on the Lightcone is that the momentum available here is not the original lambda squared that I put in as my sort of truncation lambda squared, but there is a multiplicative factor associated with this momentum fraction. So that means that when I look at the contribution at finite energy truncation of this diagram, I get the piece that I want, right? Some local piece. But then the problem is I also get the state-dependent log of x piece, right? Which depends on the momentum fraction carried by this particular particle here. So I won't be able to renormalize the theory, again, just by getting rid of this one. I need to worry about these log x pieces. But what's good about the Lightcone is that it's kind in the following way, that the kinematics of the Lightcone say that it's the same piece, even at higher order in perturbation theory. So if we go back to this picture that I drew before, then it doesn't, previously we were worried that there's dependencies here that happen depending on where these bubbles are with respect to these sunset guys are with respect to each other. But the point is that because this fraction is the same, doesn't matter if I take this sunset and I slide it around along this line, or I take this sunset and I slide it around along this line, we get the same contribution. So here it will always be the momentum of the minus momentum 1 over the total momentum, whereas for the other guy here, it'll always just be its minus momentum with respect to the total momentum, wherever this sunset is with respect to anything else. So in a certain sense, you don't get, as far as only since you're just looking at this log, you're not seeing dependence on these spectators. It essentially is the same contribution independent of what, so if you're looking just at this guy, he only gets this contribution, and it doesn't really matter what the other spectators are doing. So the good news is that you only need to calculate this contribution at order g squared. So it's a state-dependent counter term, but once you calculate it at order g squared, you're essentially done. So here's our Hamiltonian. It will contain the Hamiltonian of a free scalar. So we're going to start with just a free massless scalar. So that's our CFT. And then we're going to have relevant contributions. We're going to have this state-dependent contribution, which is non-local. But also we're allowing ourselves a local counter term here. Of course, it's up to us how we decide to parameterize our bare parameters. And it turns out that adding this local counter term is useful both for truncation and for finding the Ising universality class. Okay, so now we have a prescription for how to deal with the renormalization issue. We next should ask what basis should we use to understand the Hilbert space. Maybe I should stop before that just to make sure there are no questions. Okay, good. So now we have to face the second problem, and that's kind of the rapid growth in the number of states. And so, for example, here I'm just going to steal this very nice plot by Elias Miro and Hardy, where you're looking at the number of states on an L by L torus. So if you were using just the Fock space basis, just to give you a sense of sort of the size of the basis, well, here we have the x-axis, the truncation energy that you want to impose, measured in units of the mass. So here the free particle mass is set to 1. And so you would likely want to have the truncation energy to be about 10 or maybe somewhere between 10 and 20, let's say 15, just to be able to both extrapolate and, to have the truncation energy be larger than by your parameters that you put into the Hamiltonian. And at the same time, if you're looking for a fixed point, then maybe you'd want the volume. So here, these are shown for different volumes, right? This is a volume of 4, volume of 6, a volume of 8. So this is a 10 by 10. So perhaps you'd want to be at a truncation of 15 and a volume of around 10. And you see that, when you consider this, you're looking at quite a few states, like maybe 10 to the 8. Well, of course, it depends on precisely what your truncation energy is, or what your and what your volume you think is appropriate to do physics. But you see that you're kind of looking at quite a few numbers of states. And so at that level, when you're dealing with 10 to the 8 states, you have to be quite sophisticated at manipulating them and storing them, and it becomes harder to, for example, calculate different observables. So that gives you a sense of sort of the complexity of the issue in 2 dimensions. So what we're going to do is we're going to try a different kind of approach called conformal truncation, and see whether or not we could get the right dynamical range, and how many states in some sense that dynamical range requires. So the approach here is you consider free massless scalar CFT, and you build a conformal basis of the Hilbert space in momentum space. So what does that mean? So first, because this is of course a CFT, you could choose a set of operators that are orthogonal, right? Because of radial quantizations, you can always choose a set of CFT primaries where this is just a delta ij, and here this could have spin, and so there could be some complicated polarization. But the important thing is that the 2-point functions are diagonal in this basis of operators. And so what you can then do is, for each one of these operators, you act on the vacuum when you Fourier transform, and that gives you, in fact, a state. And the whole point is that because the 2-point function is orthogonal, these states created by different operators will also be orthogonal. And the states are, of course, labeled by the 3 momentum P, but because we're going to conserve momentum in the interactions, the spatial part of the momentum doesn't really matter. All that matters is this new label, which is just the P squared. So this is some physical state. It has a positive P squared, which I'm going to call mu squared from now on. And so each of our states is essentially parametrized by the operator. And this could have, of course, various spin indices and the label mu. Okay. So these sets of operators, that set of states form a basis. They have an inner product, which is diagonal on the operator basis. It's diagonal in the mu labels, and it's related to the spectral density, the Callan-Lehman spectral density of the operator. That is to say, it's just the Fourier transform of the Whiteman 2-point function. So that sets the inner product on our basis. And so far, we are formally at least in infinite volume, right? So, this basis is not, you don't need to be in finite volume to kind of think of this basis abstractly. However, of course, you need to be able to calculate and put this thing on a computer. So in practice, you need to discretize this basis to be in order to compute. So, of course, there's a lot of freedom in how you do this. We can choose different functions, so we can take these states and we can smear them with some discrete set of functions. We introduce here a UV cutoff. And so we have now a discrete basis, which is labeled by the particular operators and some index on these functions. And there's some freedom as to how you want to choose these functions. For this work, what we've done is just chosen something quite simple, which is just have these guys be bins. So they're essentially just bins. They have a support between, say, mu I minus 1 and mu I. You could choose these endpoints, and everywhere else they're 0. So so our we're just binning basically the mu label in some sort of discrete chunks, and these the set of bins is labeled from 1 to some Imax. So to kind of give you a picture of like what this looks like is, if I were to calculate, if I were to take the spectral density and I were to integrate it, so this is something that is we're going to use over and over. When you have a discretization, it's easier to calculate the integral of the spectral density, because then it's just the sum over your discrete set of states. And so here I'm just showing you an example of what it is that what we have in mind. We're essentially choosing where these bins lie. And so some continuous spectral integral of the spectral density is instead represented as this kind of step function in our bin basis. And we have the freedom of choosing the fatness or the width of these bins. And so the way that we do it is that we tend to, we choose some parameter R that biases towards the IR. So, we choose the bins to be sort of more narrow in the IR and sort of fatter and fatter as we go to the UV, because the idea is that we are trying to reproduce the IR states and we don't really care too much about what the UV is doing. So in this context, really what we have at the end of the day is some number of bins. We choose some sort of IR resolution and we build it up from there with these bins until we get to some UV scale. And so for this work, we're just going to use 65 bins, which are finer in the IR than in the UV. And these bins span the sort of the lowest bin here is going to be like 0.5 in units of our bare mass M. And it's going to go all the way up to, after 65 bins, to basically, well, 1,400 or so times M, right? So that's kind of the range that we are exploring in this mu variable. Okay, but it's very important to emphasize that this, yes, question.
So on the previous slide, is there some reason that you use discrete bins as opposed to like interpolating? Normally if you're going to calculate an integral or approximate an integral, you do much better with like a quadrature rule or something.
Yeah. I mean, we've done, we had polynomials. It just happened to be easier because at the end, I mean, what these bins are all about essentially parametrizing the kinematical part of a 3-point function in momentum space. And so it's just easier to do the integrals, like if you just have like a bin. So it's just more of a practical question as opposed to, but there's not, we could be a more clever choice. For sure, this is not necessarily the best thing. One could try polynomials or, as you say, some other interpolating function. We just chose this because it happened to be easier to deal with. And as far as we can tell, we don't have a issue extrapolating like in this particular thing. But yeah, I'm not suggesting it's the only or the best way to do it. But what's important though to understand it is that ultimately this set of bins and this sort of window of energies in mu or range in mu should not really be thought as the real UV cutoff, right? In the sense that it's not really the central truncation parameter. So the truncation that we're proposing in some sense is quite bizarre in the sense that it's really a truncation on the dimension of the operator. Right, so we have some set of operators that we binned in some way, but really the core of the truncation is demanding that we only look at operators whose dimension is less than a certain delta max. In other words, what we're doing is we're truncating on a dimensionless parameter, which makes this truncation admittedly bizarre. So, but it is the case that at least qualitatively, it is rather this parameter that is sort of like the energy truncation of a traditional Hamiltonian truncation program, in the sense that, first of all, the basis size grows exponentially with this delta max. And also, as we will see, the dynamic range that we can get in energy or in position or whatever it is that we're interested in physically also is actually determined by delta max and not at all by this parameter here, okay? So maybe to emphasize this again with a picture, it helps to just draw like a holographic picture that we've all seen many, many times. So this is kind of ADS, and the ADS has some sort of UV brane or UV cutoff, and it has some sort of IR brane of IR cutoff. So these are set by our lambda UV and lambda IR parameters. And then the truncation that we suggest is really keeping bulk fields with masses that are below a certain maximum. So, you know, you should think of this as the stage, and, you know, in a sense, these are the curtains. So the curtains have to be wide enough so that you could, something exciting happens during the play, but the excitement is all about the actors that are in the play and not sort of the size of the curtain. Once it's wide enough, it's good enough. So, you know, this is simply to emphasize that in a sense, the convergence in this delta max parameter is subtle. It's not something that one could estimate by dimensional analysis. So usually without truncations, you really have a truncation in energy, and you could do some dimensional analysis estimates as to, for example, if you integrate out energy states above a certain energy, what are the kinds of errors that you expect, right? Whereas here, it's just more subtle because you really are truncating on a dimensionless parameter, and its effect on dimension-full scales is not at all obvious. Of course, you know, so for now, you know, I think this is a very important and interesting open question as to precisely how do you quantify this convergence. But I should say that from now on, I'm going to sort of treat this problem as a kind of numerical experimentalist, and I'm just going to quote for you the results. And so I won't have much more to say about the rates of convergence besides the fact that we will numerically demonstrate, at least for certain quantities, what they are. Yeah, so that's just where things stand. And the only thing I could say that, you know, in a certain sense justifies this approach, even though it's very important, I think, to figure out the convergence, is simply that, you know, because there's an exponential growth in the number of states, in some sense, we start with some computational ability and we get to some sort of delta max. And, you know, with more computational effort, we will be able to maybe double delta max if we try, but we won't be able to ever multiply delta max by an order of magnitude. So in a certain sense, you know, things already have to sort of start converging from the get-go, and then of course you could push it further and improve the convergence rate. And indeed, if you knew the way that it converges, then you could, you know, correct for the leading violations due to delta, you know, due to truncation effects. So that's important. Okay, so let me now say a few words about building this basis. So what does this basis look like? It's essentially just a bunch of derivatives, right, that are acting on the field with some set of coefficients. And, you know, these derivatives can be in the minus or in the perp direction for each one of these fields. Now, for technical reasons, it turns out that on the light cone, the matrix element associated with phi squared is actually divergent. This has to do with the fact that the dimension of this operator is less than d over 2 or 3/2 in this case. And so we have to go to a basis that we call the Dirichlet basis, which requires that there is at least one minus derivative. So our operators are not strictly primary. However, they are finite combinations of primary operators. So morally speaking, it's essentially the same. This is just a technical point. But the kind of annoying thing about it is that we are breaking up, if you want, multiplets, conformal multiplets, as far as Lorentz invariance is concerned. And so now we have to go and calculate the Gram matrix for these states, as well as the matrix elements, the phi squared and phi to the fourth. And here is where our choice of basis is much more complicated than, let's say, a Fox-based basis. And that's the fact that computationally, this is non-trivial to do, even in a free CFT. So essentially, this is sort of telling you that extracting, let's say, the OPE coefficients, even in a free CFT, is something complicated. Now, maybe, like, you know, you might be surprised, isn't this theory integrable? But, you know, you should take integrability a little bit with a grain of salt because, you know, in a sense, there's still an exponential number of states. So in any given context, it's not obvious that it will be computationally easy to calculate the integrals of motion. That's one of the ways you can think about it. In general, in fact, if you choose some random initial state, it's actually non-trivial to calculate what happens to it, even if in an integral theory. So for Fock-space states, it's very easy, but you know, for some other kind of state, like a CFT state, it may be hard. And so, you know, word to the wise, we lost some amount of time, I guess, because we thought, okay, why don't we just use Fock-space states? These are the easiest ones to compute the CFT correlation functions, but that turns out to be not the best way to do it. And in fact, what we learned is it's better to use as much of the CFT structure to compute as you can. So in the context of 2 dimensions, essentially the best technique is to use a radial quantization method. So you basically use the full power of the CFT. And here's like just as a plug, we you know, this is a review that we wrote recently together with Nikhil, Liam, Zuhair, Matt, and Yuan. And it's in it, we essentially developed these radial quantization methods to efficiently calculate these various matrix elements. And this is kind of, this review is intended to be kind of, if you like, user-friendly, it's self-contained, but in it are the various different methods that are compared to each other. And also in it, we describe in general how in 2D you can calculate when you're at least starting with a free theory, with a Lagrangian field theory. So in it, you could, you know, are the basic ingredients for scalars, fermions, and gauge fields. So if you want to learn how to use these techniques, kind of this is a nice place to start. And we also provide a Mathematica package that has various examples worked out and helps you to like put together your own code in the future. So, but in this 3D context, we don't have these tools because the kinematics is much less understood, in the sense that, first of all, we don't, even for the case of CFT, we don't know, we don't have expressions for, you know, arbitrarily spinning 3-point functions in momentum space. And also we're in this Dirichlet basis, which recombines them, although that's less important because we, in principle, we know the map from the CFT primary operators to this Dirichlet set of states. So we had to resort to a kind of a more simple Wick contraction method. And so what was very crucial is this paper here written by Nikhil, Zuhair, and Matt, where they worked out various expressions for the momentum space correlation functions. And we had to use a few more tricks in order to push this forward. And so for this work, our truncation is going to be delta max of 16. And this truncation is, at the end, we'll have like essentially 545 primary operator states. So we are restricting ourselves to even parity. So, you know, and essentially at a first pass, we found that this is sufficient. And given the fact that we're using this 65 set of bins, altogether, we have about 35,000 states. And it's worth emphasizing that, you know, we've been, again, we haven't done we could improve the method with physics by not just by using Wick contractions, but doing something more sophisticated. And also numerically, all of our results, like basically generating the matrix elements and the basis, which is the majority of the time, you know, it takes a few days on a laptop using Mathematica code. So it's not really something which is very computationally intensive. So the computational component is quite minimal at this point. So, you know, we believe that, you know, we could go to, you know, higher truncations without a problem. Okay, so let me now report on our results. So, okay, so the first thing you want to know is basically, is our basis healthy? Does it do the right thing? And what are kind of the dynamical ranges associated with it? So we take our free CFT and we add a mass term to it. So it's still a free theory. And we calculate this integral over the spectral density, so of local operators. And so this is what it looks like for operators phi squared, phi cubed, phi the fourth, and phi the fifth. The black line is the expectation from theory, and the blue stuff is our data. And so you see that, you know, it agrees pretty well over a range of energies. In fact, even when it's kind of crapping out here in the UV, it's not that it's doing something completely random. It is sort of trying to follow the curve. But it's definitely the case that you are losing resolution as you go into the UV, and that's precisely what you know, I was alluding to before, that 1,400 is obviously nowhere near the actual truncation energy. The truncation energy from these particular observables is maybe something around 20 or 30 or maybe something like that. So in fact, when you look at 30, you see that all these different spectral functions are pretty close to what they're supposed to be. So it's in some sense rather conservative to say, at least from these point of view of these observables, that the truncation is 30. In some sense, it's a bit higher because it's not that at 30 you're getting order 1 violations, but so it's, you know, we're just going to sort of think, so it's sort of sensible to think that we have a truncation energy of about 30, at least as far as these observables are concerned. So that's good. For the IR, okay, so here it's a little bit hard to see what exactly is going on in the IR because the discreteness becomes more apparent. And so it's actually easier to look at the position space correlation function, because when you look at the position space correlation function, which has the, you know, with the Callan-Lehman representation, you are looking at some smooth function. So now you can compare a smooth function to a smooth function, and this is what you get. So again, the black line in here is the theory expectation, and blues is our curve that we get from our data. And you see that, again, and this dashed line is approximately where the data and the theory deviate by 20%. So beyond this point, they deviate by 20%. Or this is, and oh yeah, the insets are always the ratio, I forgot to say, between the data and the theory. So again, we see that we're doing not badly in the sense that, you know, there's some effective IR cutoff here, and it's something of order 10 over m. So again, as far as these observables concerned, we seem to have a dynamic range, which is sort of 30 m, and a cutoff like in the IR, which is, of course, is not the same as being in finite volume, but some effective IR cutoff beyond which we're seeing truncation effects, which are of order 10 over. So this is sort of our window. Okay, so now that we've sort of checked the free theory, let's check the perturbation theory and just make sure that our sort of matrix elements are healthy. So we start just by computing the g squared and the g cubed contribution. So on the Lightcone, the only contribution at order g cubed is this particular diagram. And again, we could do is we could try to see how well we match perturbation theory. So here on the x-axis, I have this lambda UV scale, which we can dial to be quite large, because here, note that we only need 3 particle states in order, this order of perturbation theory. And so in fact, we can go to both higher truncations as far as delta max is concerned, and also higher truncations as far as our sort of energy curtain is concerned, right? So we see that we are, you know, as we increase the truncation, we're getting closer and closer to the expected answer. And if we take our final point here, at every given point, and extrapolate it in delta max, it seems like there is a 1 over delta max squared extrapolation. And if we perform this extrapolation, we're within 2% of getting this sort of UV sensitive log contribution, and within 1% of getting this number here for the G cubed. So it seems like, you know, our basis and our matrix elements are doing the right thing. Okay, so now we go into the non-perturbative regime. And so here I want to take a brief technical detour and explain that we don't quite perform the renormalization procedure that I sketched out. So originally, remember that our state-dependent renormalization was is really just the idea that we should get rid of this log. So we create an order G squared piece, which is just getting rid of the state-dependent log. But the problem is that, you know, we're not in, if you were using a Fock space basis, this would be probably the way to go. But because we are using this conformal truncation and we have these operators, we're not going to fully reconstruct this log or this coefficient perfectly. So in fact, what we're going to do is something a bit more brute force, which is that we're just simply going to remove the entire order G squared shift at our chosen truncation level. That is to say, our state-dependent term is really just this thing calculated. So we, at a given truncation level, we calculate in second order in perturbation theory, old-fashioned perturbation theory, we calculate this diagram and we introduce this as a counter term, which is non-local and depends on this external state. So we're basically removing, you know, anything that this could possibly generate. And so this is just a better fit given our truncation, but it's of the same spirit. So now this is our total Hamiltonian. It's got the as we said, the CFT has these relevant operators and also the state-dependent piece that I just explained, which is just this brute force removing everything at second order. So first phenomenon we see is that the gap closes as expected. And here in this particular plot, we chose this local counter term to be sort of what the naive contribution would have been had we just had a regular divergence, right? So this is some choice. Of course, it's just some number. We can choose whatever we want, but this is the number that we chose. And we see the gap closing. So here, this is the one particle state. Here's where the Z2, so this is the Z2 odd. This is where the Z2 even continuum starts. So this is sort of the two particle state. And this is where the Z2 odd continuum starts. So this is something we call the three particle states, right? So the gap closes, but how well does it close? You know, so this is a theory with a repulsive interaction. And so as the gap is closing, we expect the ratio of the one particle state to the, you know, onset of the even continuum and the onset of the odd continuum to always be fixed, right? This is always supposed to be, the ratio has to be 4, and the ratio has to be 9 as we approach the gap, right? So what we can do is we can measure this. And so here we're plotting as a function of M gap over the coupling constant, this ratio, the ratio of this two particle threshold over 4 times the one particle, and the ratio of this 3 particle threshold over 9 times the one particle. It's supposed to be 1. It's not going to be exactly 1 because of truncation effects. But you see that, you know, here we're comparing the ratio, the difference between having our state-dependent counter term and not having a state-dependent. So if you have just this old state-independent counter term, and you see that, okay, when in the perturbative regime, when the mass gap is large compared to the coupling, of course, they sort of, the ratios agree. But as the interactions become more important, we see that without the state-dependent counter term, the ratio diverges, right? So it moves away from what it's supposed to be, and it moves away at the second, basically, the perturbation theory breaks down. So very dramatically here, a little bit less dramatically here, but still. And so, but with the state-dependent counter term, the ratio seems to be okay, all the way up to maybe a half or something like that. So note that this is zoomed in. So we're still, even here, kind of within 20%. So the upshot is that the state-dependent counter term is essential to this story.
So sorry, I mean,
Yes.
I couldn't see what was the x-axis here. It's behind me.
Oh, sorry. Or did I?
Because it was behind your.
Yeah. Yeah. So the x-axis is maybe I should do it like this and scroll down. The x-axis is just the mass gap over the coupling.
I see.
So
But so when you go to very weak coupling, so it's to the right in your
yes,
plot,
yes. So
even there you don't go to one, even in the.
right, and that's just because I'm my basis is this conformal truncation basis. So the massive eigenstates are not perfectly reproduced, right? So I'm not starting exactly at 4. I'm starting close to 4. I'm not starting exactly at 9. I'm starting close to 9.
I see.
But it gets better as you go to higher truncation. Yeah, that's right. Okay, good. So I won't say too much about the dependence on the coefficient of the local term. So you could vary this coefficient, and in principle, the physics should be independent. But the reason we included it is twofold. One, in practice, we see that the fact that we chose this coefficient to be 1 in terms of this log, let's say, which is some arbitrary choice on our part, was just some generic choice. We didn't have to have it to be 1. It could be a half. It could be 2. But very clearly, you see that if I chose it to be too large or too small, the deviations would be more severe, and so I can stay within this regime, but I can't really explore arbitrary coefficients without encountering more significant truncation errors. So I will put a little plug for the next talk in our Bootstrap series. So the CISA group came up with a new result, which is they're also in 2+1 dimension, where they make some very specific predictions about the minimal coefficient for the gap closing. So one part is just the truncation aspect. The other part is physics in the sense of like infinite truncation. Do you actually reach the Ising universality for any choice of this coupling? And I'll refer you to Marco's talk next week, where he's going to talk about it in more detail, but the expectation is that you don't. And I think as we increase the truncation and and after we perform our dictionary from equal time to Lightcone, we should be able to make contact with their result. But right now we just don't have the resolution. So qualitatively, we see what they're saying, but quantitatively, we're not in the position to kind of make sure that we agree numerically with their prediction. All right. So those are just the basics, the gap closes, but the deliverables, I think, which are exciting in this method are really the correlation functions. And so we could study them. And of course, we could study them now at strong coupling and you see now, for example, phi squared or phi to the 4th at different truncations. So again, this is the integral of the spectral density, but there's very little that we can say about this because it's unclear what we're comparing, right? However, so this is some generic strong coupling. However, near criticality, we know what's supposed to happen in the sense that near criticality, we expect every odd operator to have an overlap with sigma and every even operator to have an overlap with epsilon. And so we expect universality. So up to a constant that we cannot determine, we expect phi squared, phi to the 4th, and phi to the 6th to agree in the IR, and we expect phi cubed, and phi to the 5th to agree. So here, of course, we allowed ourselves some constant for each one of these, but when with an appropriate constant, you see that they are in fact overlapping in the IR, so in the region below 1. And then, of course, in the UV, as they begin their RG flow up towards the free scalar, we see deviations. So first thing we see is universality. So that's nice. Also, we could look at this more detail in position space. So again, we look at the same correlation functions, but transformed to position space, and now being close to criticality where the gap completely closes. And so again, qualitatively, now this is a log-log plot. We're plotting the position space correlation functions. And we see that, of course, They agree in the IR. That was the same information that was already contained in the spectral densities. But moreover, there is, you know, maybe something like an order of magnitude, maybe a little bit less, where they also happen to have, appear to have a power law kind of dependence, and we can fit this power law. And what we find when we fit this power law is 2.4. So if we, or another way of representing this is that if we take our data and divide it by 1/x to the 2.4, then, you know, these guys, where they are, the universality begins is where they begin to overlap. They begin to flatline with this choice of 2.4. Of course, as every bootstrapper knows by heart, the expectation is 2.83. So of course, we're not claiming that we are at some kind of truncation, which gives us very high resolution. But you know, the idea is that we are seeing power law behavior, and it seems to be in the right ballpark. So as we increase our truncation, and as we are going to move this front where the shutdown happens due to the truncation further out, and model it better, hopefully we can get like a more precise measurement on the critical expo. Okay, so then there's also the trace of the stress tensor. So we expect the trace to vanish for a CFT, but there's just a slight subtlety for us because we also have this, you know, besides the trace, of course, gets a contribution from the relevant operator phi squared and phi to the fourth, but also we have our state dependent piece. And in particular, within our state dependent piece, even though it has this sort of non-local contribution, it also has a local contribution, which we included. Now, this local contribution, we know that at delta max equals infinity, it's going to asymptote to our naive QFT expectation, but at finite truncation, it won't quite be that. So it turns out that you could measure this using the equation of motion. So you take the equation of motion, which contains this parameter, and you can project the equation of motion. So p squared phi is equal to this thing phi plus g over 3 factorial phi cubed. You project it on the free particle state, and all these terms drop out, and you wind up with the fact that the state-dependent counter term is essentially just the one particle matrix element of this state-dependent counter term, and you can go and you can measure it in the UV once and for all at a given truncation, and it happens to be 0.89 times this thing. So not quite one, but getting there. So once you fix this delta t, now your trace is completely determined. And so now you could check whether the trace vanishes. And here's what you find. So at zero coupling, you know, it's basically just phi squared, but as you push yourself to the critical point, you see that the trace indeed collapses here. And in particular, note that, you know, each of the individual contributions, they're not vanishing at all. It's specifically the combination of these guys, which is associated with the trace, that is shutting down. And so this is kind of nice evidence for a CFT. And in particular, this is precisely the kind of observable that would be kind of hard for the lattice to calculate, because there's no canonical way that to define the trace of the stress tensor. But for a Hamiltonian truncation method, one could define the trace of the stress tensor and see that indeed it vanishes. Okay, so final observable before I end is one could again look at the trace, but now in position space. So the trace near the critical point has the leading contribution, which we can tune to 0 as we close the gap. And it has this sub-leading contribution that comes from the fact that, you know, of course, we are in an RG flow, so we're not exactly at the Isaac CFT. And so when we look at that, again, we have the UV region, and then it transitions and more or less in the same sort of region where we saw universality before. So previously it was between 1 and 5. Here it's between, say, 2 and 7. We seem to be finding scaling behavior, and that scaling is 6.1. And whereas the expected behavior is 6.83. So again, like, I'm not claiming that this is a careful measurement, at all, but but it's just that qualitatively it looks about right, and again, hoping with increased truncation that we'll be able to zero in and extract this power law more precisely in the future. Okay, so let me conclude here. So here I presented our first passes at a non-perturbative RG flow in 2+1 dimensions using the method of Lightcone Conformal Truncation. And I've shown you some evidence that we're beginning to probe the 3D Ising. And so even with the kind of low truncation that we started out with and that we hope to improve in the future, certainly we need to push to larger truncation, make use of more clever use of CFT kinematics. It would be great if someone would compute spinning correlators in momentum space, so we could actually use this and take and make use of the full power of radial quantization. That would make the truncation more, the matrix element calculation more efficient. And okay, of course, there's the important question of understanding the convergence in delta. And in particular, to me, it's still kind of an amazing that we got the kind of dynamic range that we saw. So I don't really understand why is this basis that efficient. I mean, in the sense that, again, like you could have worried. I mean, I'm not saying it's whether or not it's computationally efficient is a different question, right? It could be that computing this basis is difficult, and so there's a conservation of difficulty. Let's say you take the Fock space basis, you need like 10 to the 8th states or whatnot, but computing, but you need to store them, but computing the states themselves in the matrix elements is very simple. Whereas here there is computational difficulty in computing this basis, but it's kind of amazing to me that ultimately the bins that we use, the 65 bins, they're just parametrizing some kinematic structure, right? So really the dynamical part is contained in the fact that we're using these 545 conformal states. So there's a 550 times 550 matrix, which is really the only thing that we're really using to obtain these results. And so it's just an interesting theoretical question. I'm not really sure I understand, like, why is it able to see this kind of dynamic range? What makes this basis kind of useful, at least for these observables that we've calculated here? Okay, so the very interesting question of convergence. And then there are kind of natural targets to extend this method. Sort of the immediate targets, which do not require too much new technology, are the O2 model, which has some interesting physics, and one could even study, correlation functions that not in the vacuum. So you could look at conductivities, and you could look at all sorts of interesting physics with the O2 model. And also, we could, instead of adding a real scalar, we could also add a real fermion and consider a SUSY model. So that could be a fun thing to do, because there's supposed to be a flow, and there's also supposed to be an interesting IR fixed point to explore. So these are things to do for the future. Thanks.
Thanks, Ami. Questions? Okay, I'll start. Have you tried looking at 4-point functions? Is that feasible?
Yes, in principle. I mean, we've not considered anything more than a 2-point function, but in principle, I mean, we have the states, right? So as we increase the truncation, we could, in principle, look at 4-point functions. Why do you ask?
Well, they're not going to be automatically crossing symmetric with this approach, are they? Or are they? That's like, how does crossing symmetry?
Right. That's right, because you're trying to, in fact, this is something that's is a very interesting question, because yes, you are kind of summing over a set of states, but you don't have the full basis of states, right? So it's in fact, we've already sort of seen effects of this because um, in a certain sense, when you sum over the basis of states, like say, even when you're trying to get to this log singularity, the log singularity that comes with, if you were to consider some phi to the fourth OPE is only, is actually softened because you're not including, for instance, in the cross channel, all the states. So effectively, there's a delta max. So another way to say that this lambda UV parameter is not the real UV cutoff is that, for example, in some singularity that happens when you move phi to the fourth, two phi to the fourth on top of each other in one channel, you're only reproducing it in the cross channel partially, right? And so the delta max enters in this UV resolution. But indeed, that's an interesting thing to consider, right?
I guess I was asking because one of the most interesting potential applications that you could get out of this is to think about transport.
Yes.
Is to calculate transport, which can't be done any other way. And there are various ways to do that. One is by looking at 4-point functions.
Well, I mean, one thing you could try to do, I mean, this is something we're trying to do actually in the 2D example, where of course everything is easier, is you could look at hydro in the sense that you could take a time-dependent correlation function, right, in the background of some ETH-like state, or a state that you believe like ETH. So you could hope to extract some kind of hydro from that.
Yeah.
And I don't know, that might be simpler than looking at a 4-point function. That's something we're trying. So
I thought that I was thinking that was the same. What's the difference? A 2-point function in a state, or a 4-point function?
It's the same. It's just that you're fixing. Yeah, I mean, you're just instead of having a local operator create something, you just take the state. So
I see. Okay, yeah.
Mechanically, it's easier, and it's it's also one of those things where you can then then you're going to get noise, and so there's also quite natural to average over some micro band. So this is stuff we're playing around with. I mean, at least in 2D, all I can say for now is that we are seeing Wigner-Dyson statistics, but it's early before I can report on anything.
You mean for the excited states?
For the excited states, yeah.
For the energy eigen,
for the energy eigenstates. In fact, they're very quickly transitioned for Poisson to Wigner-Dyson the second we turn on the coupler. But it remains to be seen whether we have enough resolution to see hydro modes, for example.
And this statement about the spectrum, this is about the spectrum of primaries, I guess?
No. The spectrum, the eigenstates of the Hamiltonian once we diagonalize, right? So the primaries are just the primaries of a free scalar CFT. So this is the energy spectrum of the interacting theory in the presence of a quartic coupling.
You might think that would be so controlled by conformal invariance that without sort of deconvolving out the conformal invariance, you might not expect to get Wigner-Dyson statistics. At least.
Well, I mean, in terms of particles, that, if you have enough particles, then perturbation theory breaks down. So there's no way that there's some regime, it's a relevant coupling. So maybe if you have in some energy regime, you're back to kind of perturbative description. But, for many particle states, you have non-perturbative physics, right?
Yeah.
And so you are seeing that even first. So, I don't know how much you're following all this Higgs explosion and stuff like that, but even a small coupling is actually significant if you have enough particles, right? So it's actually interesting that you do see Wigner-Dyson statistics.
Okay.
Question on is it possible to understand the convergence with delta, at least in perturbation theory?
Well, it's certainly true that we understand the convergence in delta for the free theory. So the fact that we get 1/, so we analytically understand it. We have analytic expressions for the actual eigenstates for the case of two particles, and we have a kind of qualitative understanding in the case of n particles as far as just a mass perturbation, because they're at the end of the day, they're just polynomials on the Fock space, and they're the polynomials on momentum space, right? So in momentum space, like at least for free particles, those are particular momenta, Fock space states are actually the eigenstates. And so in some sense, you're just asking, how do polynomials approximate delta functions? So in that case, we understand the convergence pretty well. So the fact that it goes like 1 over delta squared for a massive theory, or 1 over delta squared in the perturbative regime, is something we understand. But how to argue how it should go in the non-perturbative regime, I don't know how to do that. But also the way I'm not happy with the way I understand it. Like the way I understand it is very specific to kind of the Fock space representation of these operators. Like I would like to know what the answer is from a more CFT way of thinking.
And so in this respect, so in the ordinary like Hamiltonian truncation position space, etc., like if I go at second order in perturbation theory, the convergence is controlled by some short distance, short time limit of some 2-point function of the interaction, etc. So this is what is lacking in this case. There is no way to express this.
Right, because it's like the idea that you're integrating out stuff and that gives you something local is sort of true holographically in the bulk, but it's not actually true in the actual theory, right? So you have to somehow take your holographic intuition and translate it into something more clear. I think it's a very interesting question. This is kind of the thing that is definitely should be sorted out.
So maybe I can follow up with a comment to Marco, because so this parameter delta that it seems to be so natural from the CFT perspective, if one thinks about this from some like pedestrian particle physics perspective, it's not natural at all, because it encodes, you kind of package in one parameter delta two very different things. One is the number of particles in your state, and the other is the dependence of the wave function of these particles on momenta. And in the old days, when people were playing with this naively, they usually kind of treated these two parameters separately, and they tried to understand if how much resolution you need in one of these parameters and how much resolution you need in the other of these parameters. And it was not really obvious that that they had to scale in some consistent way. But here you say that you believe that they have to be scaled together within this delta. So that's, I mean, that's not obvious. I think it's still not obvious. It's kind of, it's still a smart guess. Might be true, might be not true. Yeah. I also had a question actually. So I know, I mean, you always you like to think about these real-time questions, but for example, just as I know there are these people out there in other communities I recently discovered who like challenges. So apparently, like some of the things that I wrote in my early Hamiltonian truncation papers as a challenge, they were picked up and so on. And I was surprised actually that anyone was paying attention to these challenges, but people actually did. And they got stimulated to do something. So I was thinking if you could use your approach to compute some, I don't know, maybe like, well, take a 2-point function of some operator which interpolates between Gaussian theory in the UV and CFT in the IR in this whole range.
Yes.
So you probably can extract a concrete prediction for this whole function.
Yeah, that's what we're giving you.
Okay. Well, so that's, you could say, well, this is a concrete prediction. I have a 2-point function in the full range from UV to IR, and that's something that
yeah, Yeah,
that the
so-
lattice people should have
Yes. So
no problem of measuring if you like ask them and
yes,
if
in
you
fact, I
pose this
am.
as a challenge. Yeah.
So I'm talking to, as you probably know, local here, we have Anders Sandvik, who's kind of a world expert in Monte Carlo for spin systems. And we're precisely going to try to do this for the transverse field Ising, as they call this thing. So they should be able to tune their transverse field Ising to criticality. I mean, they won't, I don't know, I mean, what you say is a bit harder. I mean, I don't know, like, I guess they could also, I could discuss with him trying to really do this for the full RG flow from a free scalar. But at least I think, given the fact that, you know, the 3D Ising perturbed by an epsilon is unknown, right? So even
I'm sorry, but what are you exactly? Yeah, then you're doing something else, not what I.
Yeah, I'm not doing the free theory. That would, yeah, I have to talk to.
But that's what you're computing here. You're starting with free theory in the UV, and you're ending up with CFT in the AR.
Yeah, that's hard, right? For a lattice, that would be.
Why is this hard?
Well, because it's a double fine tune. Well, I mean, I don't know. They have to start from a free scalar, right? So typically they start from some spin system, where they have very efficient algorithms. I mean, I don't know. I guess I could ask Anders.
I mean, if you want to reach high precision, it's hard. If you just starting from free scalar just means, okay, you have to take your lattice spacing maybe a factor 10 smaller.
Yes, but you know,
it's something if you just do classical statistical mechanics, not from the quantum point of view, which Sandvik is likes, but from like Rich Brouwer point of view, if you can convince him.
Yeah. No, I can ask also Rich. I mean, that's right. I mean, I think that as long as they get to some significantly large, I mean, because in the context of their calculation, our dynamic range, right? Because since we have a cutoff of like, let's say 30 in the UV and a cutoff of like 10 in the IR, that's like, they need a lattice of size hundreds.
Yeah, hundreds, but hundreds in 3D is not a big deal.
Yeah. So I think they should be able to do it. I mean, the only we should be able to calculate it in position space, and they should be able to just directly measure it in position space, I guess. I mean, it's a little bit harder for them. I mean, one of the things that Anders is working on is like he measures these correlation functions in the Euclidean theory, and then he attempts to analytically continue to extract the spectral density. So that requires some finesse, but one could definitely measure things in position space and directly attempt to
but Anders can do it, forget it, because he only does quantum things,
right. But I mean, yeah. Do you know, like, people? Yeah, I guess I should ask how well are people.
Well, for example, this Rich Brouwer, they were doing for a long time this radial quantization,
right?
Where they were putting phi to the fourth theory on the sphere. Well, this in particularly, this phi to the fourth theory on the sphere, which was harder than what would be needed here, it required taking the lattice spacing sufficiently small so that the theory at the lattice scale was weakly coupled.
Right.
So that was a necessity for what they did. So.
Yeah, no, I should definitely ask Rich and see if we could compare notes. That's definitely not. That's definitely a good idea.
Going once. Going twice. All right. I guess that's it. Thanks again, Ami.
See you guys next week.